Okay, so on Friday, we started section 1.3, and we talked about conditional propositions and also biconditional propositions. As a quick reminder, a conditional proposition is an if-then proposition, like this one. If you make an A on all of your exams, then you will pass discrete math. And one of the tricky details about the conditional if-then statement is what to do when the left side, the if part, is false. And it turns out that we should regard both of those as true, because going back to the example, we know that if you don't make an A on all of your exams, then it's still possible that you could pass, like if you make B's or C's. But you could also fail. So in either case, we have to consider the overall statement is still true. Okay, so we worked through that, and then we did a truth table, a bit like the one that you just asked about on your homework, where we combined simple statements into something more complicated. And then we ended the lecture last Friday here. There we go, with the biconditional proposition. And this is the if and only if sentence structure. And the biconditional is something like an equal sign. It's true when both sides of the proposition have the same truth value. So if P and Q are both true, then the biconditional proposition is true. And if they're both false, it's also true. But if they disagree, if you have a true and a false, then the biconditional is false. And the example that I showed you was this one. It's a simple kind of mathematical proposition using an inequality. X is less than 2x minus 3 if and only if 3 is less than x. So the difference between this side and this side of the if and only if is that I've rearranged the inequality so that the x is on one side and all of the numbers are on the other. So just the sort of thing that you would have done in your algebra class. So normally we want to think about when this is true, so what values of x solve this inequality. But we also have to think about it when it's false. So what would happen if I plugged in a number that was less than 2 instead of greater than 2? Well, they still have the same truth value. This is false, but also this is false. So 2, and then you get a 1 when you plug in. Okay, so that was a quick review of what we did last week. The two kinds of new propositions. The big topic for today is this next one. This new definition. It's a little bit complicated when you have to write it out in words like this, but we'll see how it works when we do some examples. Suppose P and Q are propositions made up of simple propositions, and I'm going to give my simple propositions these names, these letters, P1, P2, up to however many I have, Pn. So as a reference, think back to these kinds of more complicated kinds of propositions where you have something complicated on the left side and maybe something complicated on the right side too. So all I'm saying in my definition is that P can be a compound proposition. It can have more than one part, and same for Q. Because most of the time when we're doing logic, we are talking about things that are more complicated than just these simplest kinds of propositions, right? Otherwise, we wouldn't really have to think very hard about it. Everything would be simple. So let's move on with the definition. We say that P and Q are two compound propositions, are logically equivalent and this gives a symbol much like the equal sign. So we'll, instead of having two horizontal slashes like the equal sign, we'll use 3 for logically equivalent. And this, going back to the beginning of the sentence, we say that P and Q are logically equivalent if P and Q have the same truth value for any values of the little simple propositions here. So essentially what this means is that they have the same truth values no matter what the values of your simple parts that make up the more complex statements, P and Q. Maybe I'll put a note down here that we think of logical equivalence the same way we think of an equal sign, like when two numbers are equals. Like if you said x is equal to 2, right? You're just saying these are the same thing. Logical equivalence is very similar, except now we're talking about truth values instead of numbers, so we use a different symbol. So next we'll need an illustration for logical equivalence, or a good example. And you might remember me mentioning De Morgan's laws back when we were talking about sets. And we're putting propositions into sets. Are you asking about De Morgan's law? Or going back to the last page, are you asking about these capital letters? Okay. So what I mean here about P and Q, I'm not thinking of these as sets, as just groups of propositions. I'm thinking of something like a more complex proposition. So like P could be P1 or P2, and then an implication and I don't know, P3. So this could be what my capital P is. And my Q could be something, and these aren't, what I'm writing isn't going to be actually logically equivalent, but just examples of what they might possibly be. So your P, your capital P is something complicated, and your Q might also be something complicated. Well,
but P and Q have to have the same truth value, right?
If they're
For these to be
logically
true.
equivalent,
Yeah.
yes, they would have to have the same truth value.
Okay.
That's right. And then how would I ask this on a test? let me scroll down here on the next page. This would be the kind of question that I would ask. Well, on a test, I would have a word, show that. So show that this statement is logically equivalent to that statement. That's the kind of thing you might see on a test. Okay, good questions. So let's talk about De Morgan's laws. So you might remember me mentioning this name, De Morgan, back when we were talking about some of the properties for sets, for set complements, actually. And we're going to run across the same name again here in logic, and you might see that they look similar to the set properties. Instead of a complement, we now have a negation, and instead of intersections and unions, we have ands and ors, well, or and ands. But the effect is the same. The negation flips the sign in the middle. So this or becomes an and this and becomes an or when you distribute the negation. So these are some of the kinds of logic laws that you might want to know, or that you might need to know. And go back to black. Grab that one by accident. Oh, let's just start over. That symbol didn't look right. Not sure what happened there. So what I need is this, my simple statement inside of here, P or Q. And then I have my two simpler building blocks from the right side, just to illustrate what I'm doing here. I'm building my truth table from simple to more complicated. And now in this next column, I want to put the negation on this one so that we have the total left side, since I'm trying to show that this first logical equivalence is actually true. And then in my last column, we're going to have quite a few on this example, I want to put the total right-hand side. So not P and not Q. Yeah. And now we fill in from the left to the right, from simple to complicated. And since we're trying to show this law is true, we're trying to show this logical equivalence, what we want to see at the end is that these two columns, the one for the left and for the right, have exactly the same truth values in their rows. So let me put a note up here before we get started. We need to see that these have the same truth values, or that these two columns are the same. So two simple propositions gives us 4 rows for the different possible combinations of true and false. And then we start filling in. P or Q is true when there's at least one true here in these two. So we'll get a true, 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 and then finally a false, since we have two falses in this bottom row. And then the negation of P switches the truth value of this column. That means we'll get a false, false, true, true. The negation of Q switches the truth values. Okay, good. Yeah, that's the right answer. We're switching the truth values in this column. So we'll get a false, true, false, true. And these are all of our simple building blocks. Next, we need to build up the whole left side. And for this one, we just have to look at this column and switch. Yes, that's the right answer, Davian, again. We switch the truth values in this column, and we ignore, well, we can ignore everything else for now. So we just get a false, 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 and then a true. So just covering these up again. We have the opposite truth values. And then to fill in this final column for the AND statement, we'll have to look for two trues in these two columns that correspond to those halves. So now we're going to ignore this and all of this over here to try to fill in. So which is the only row with a true? Two trues? Well, it's just the bottom one, right? So we'll get a true in the bottom row, but then in the other three, there's at least one false. So that means the AND is going to be false. Okay, so now we have our two columns. Let me just box these so that we can look at them. Are these the same? Yeah, they're the same. So that means that these are logically equivalent. They have exactly the same truth values, no matter what the truth values are over here. So this is what logical equivalence means. So whatever truth values you plug in for P and Q, these two more complicated statements, propositions, have the same truth values. Any questions over this first example? Okay.
It's not over the example, but I do have a question.
Okay, go ahead.
So what would happen if we ran across a problem that had the symbol for logical equivalence, and we were asked to show, show its logical equivalence, and it wasn't actually logical equivalence? Is there going to be something like that? Kind of like a trick question or something?
Let's see. So I don't think there are any questions like that in your textbook. I think it'll tell you directly. But another way to phrase this question that you will run across is to just determine if two things are equivalent. And there it could be one or the other.
Okay.
But I don't think we'll have any trick questions. This next example is actually pretty important and I'll explain maybe after we make the truth table. But first, let's just show that this one, P, or if P then Q, is logically equivalent to this other statement, which says it's not the case that P and not Q. Okay. So we have two simple propositions here, P and Q. So this truth table will look pretty close to the last one because we'll have 4 rows. And then we want to build up our more complicated logical propositions from simpler ones. This one, we already have the truth values for. This is the one that we'll have to do a little bit of work in order to get the overall truth value. So the component pieces, looking inside of the parentheses, we'll see the negation of Q is one of our components. So we might start by making a column for it. And then this negation of Q is put together with P in an AND statement. So let's make a column for that too. And then finally, we negate the whole thing. So we put the negation symbol on the outside of the parentheses. So this is how you build up that proposition from the simpler pieces. So you put, do these steps to build up the whole thing. So that's how you might want to think through your table. And then your last column, we can put this as a whole piece, since we already know the truth values for the conditional statement, if P then Q. So now that we have it set up, we can start working from the left to the right, from simple to complex. We have the same 4 combinations of truth values. Okay, and now we need the opposite truth value for this column for Q. So true becomes false, false becomes true. And now we have to put our not Q together with P. So for this, we're going to ignore Q and look for 2 trues in these 2 columns. So which is the only row with a true in it? Here. It's right there, right? As far as 2 trues or 2 false, I'm not sure exactly what you're asking, Davian. How do you know what to look for? 2 trues or 2 false? So at the moment, we're just filling in from our simplest, let's see, ignore that for now. Why are we looking for 2 true statements? Okay, I get it. So we're trying to fill in the column for P and not Q. In order for this statement to be true, we have to have a true here and a true here. And that only happens once in this row. And someone guessed the correct answer. It's false, true, false. Right, the and symbol. That's what tells us we have to look for 2 trues. The and in between. If there was an or, this flipped upside down, we would only have to have 1 true. but since it's the and, we have to have 2. Okay, so we take this column and we put a negation symbol on it. That means we take all of these truth values and switch them. False becomes true, true becomes false. Okay, so we built up this proposition. Someone remind me the truth values for this one. So ignore all of this for this second, and then just fill in that column.
For that statement to be true, P cannot be true and Q be false.
Good. So that only corresponds to this row where P is true and Q is false. So this is the only time it's false, and the other 3 are true. Okay, so is the conditional statement equivalent to this one?
Yes.
Yes, so they have the same truth values no matter what we plug in. So since these are the same, it is, or these two are logically equivalent. And before we move on to the next 2 examples, I want to explain the significance of this. And essentially, what this equivalence is telling us is that this conditional statement is equivalent to the simple kinds of ands, ors, and nots that we learned in the first section. So we can rewrite conditional statements using simpler things. So even though the if-then proposition seems like a more complicated kind of thing than ands and nots and ors, we can actually build it up out of them. So we can rewrite any conditional statement using just and, or, and not. And here at the end, we have 2 more examples to get through. The first one says that the biconditional is logically equivalent to 2 conditional statements. So here we have an arrow pointing both ways, and it turns out that it's equivalent to, well, looking at 2 separate arrows. So P, if P then Q, and if Q then P. And this is actually the reason why we use this symbol, because it's both. The arrow points both ways, just like the conditional. Okay, so we need our truth table with 2 simple statements, and then we'll build up our complicated statement from the simple ones. So we'll make a column for if P then Q. We'll make another column for if Q then P. And then we'll put them together with an and. If P then Q, and if Q than P. And then we'll finish with a column for the biconditional, P if and only if Q. Okay, and this one I'm going to do a little bit faster since we have some experience. We fill in the simple truth values for P and Q. The four possibilities. And then we already know the values for the conditional. We know that this is true unless we have a true on the left and the false on the right. So this one, and everything else is true. This one, you might remember when we switched the arrow, is called the converse of that one. And this one is false when we have a true for Q and a false for P. So that would be here, where Q is true and P is false. And everywhere else is true. Now we combine these two columns with an and. So we're going to ignore this and look for two trues here. So we get true, false, false, and then true again, where we have two trues. Okay. And now we have to think back to the definition of the biconditional. And remember, this was like the equal sign. It's true when P and Q have the same truth value. So ignore that for now and look for two truth values that are the same. So that's the first row and the bottom row, and the other two don't match, so we get falses. Okay. So now we're done. We have our columns for this part and then the biconditional, and we can see that they're the same. So a biconditional, if I can spell, a biconditional proposition is equivalent to two conditional propositions. And then in the last couple minutes, we'll do this example. And let me give this a name. So here, our initial conditional statement is if P, then Q. And this new one, I've reversed the order and I've put negation symbols on everything. And if we do this, if we start here and change it to that, this is called the contrapositive. This is another important kind of proposition that we'll see again and again. And again, working quickly, we start with P and Q, our simple propositions, and then I need to build up this one that's more complicated. So we need one column for not P. Maybe I'll do not Q first, since it's on the left. And then another column for not P. And then we'll put the two together in a conditional statement. And then my last column will be for the regular old conditional, if P, then Q. Okay. And it looks like it's 12:50, so if you need to go ahead and leave for your next class, you can do that. I'm going to finish this example. It'll take me maybe a minute or so. So do stick around if you have time. Just fill in on the left with the combinations, and then switch the truth values for Q. So we get a false, true, false, true. Switch the truth values for P. So we get a false, false, and then true, true. And then now for this conditional, we'll ignore that and we'll look for the only possible false, where we have a true on the left side and a false on the right side. So that's this row. We have a true on the left and a false on the right. That's where the conditional is false. And then everywhere else is true. So that completes this part. And next we'll fill in the regular old conditional by returning to the simple statements. And again, this is false when the left side P is true and the right side Q is false. So fill in your false there, and everywhere else is true. And once you finish, you can see that this one, these two statements are also logically equivalent. And this equivalence is important. Like I said, we'll see it again and again in the class. So the conditional statement is logically equivalent to the contrapositive. So we switch the direction and put negations on everything.